Okay, great. So I think we can start. So welcome back, everyone. Today we're very happy to have as first speaker Héctor Parra de Freitas from Saclay, and he will tell us something about tadpoles and gauge symmetries. Please.
Okay, thank you very much for giving me the opportunity to talk here in the seminars. I'm very happy. I'm going to talk about some recent work that I did with Andreas Braun, Marina Grania, Bernardo Freiman, and Stephanie Lust. And it's, as the name implies, has to do with tadpoles and gauge symmetries. So let's just get a very brief introduction. Let me see if this works. Okay, great. So the starting point for this is a recently proposed tadpole conjecture, which it essentially states that if you're doing some F-theory compactification with flux and you want to stabilize all of the moduli, you run into trouble if you want to do it generically at the generic point in the moduli space. Because as soon as you stabilize all the moduli, you violate the tadpole constraint, the tadpole bound. Instead, it looks like when you are able to do this, you are at special points in the moduli space where you have enhanced symmetries. So there seems to be a relation between satisfying the tadpole bound and having enhanced symmetries. And that's the purpose of this work is to explore this interplay. Now, I should say that most of the work that has been done in tadpole has been kind of statistical, looking at special regions in moduli space. Here, we can focus on a specific kind of compactification that has been studied in the literature and be exhaustive about this, as I will explain. We simply look at F-theory compactifications on K3 times K3, and we determine the gauge symmetries. And this is for a special choice of the flux. And the result of this is that there will always be non-abelian gauge symmetries when we are below the tadpole bound. I will also have some things to say about what happens when you are above the tadpole bound, and if you actually find certain models without non-abelian gauge symmetries. So the starting point here is to consider M-theory flux compactifications on K3 times K3. It's a product to K3s. And you put on this flux. Now, we are considering a pair of K3s, hence the quantization condition for the flux is that it belongs to the middle cohomology of this product. But we are ultimately interested in uplifting our solutions to F-theory. And for that, we consider, or rather the most general form of the flux that we have is this. There are two kinds of terms. The first one involves products of 1,1 forms. And the second term involves 2,0 forms. So essentially here we are avoiding terms that are proportional to volume forms of the K3s. And finally, at the end of the day, we will require, we have to satisfy this constraint, which is the tadpole constraint, is the n flux, so defined, has to be smaller than or equal to 24. So as I said, we have this general form of the flux, but we will in fact restrict ourselves to the second term. We will not consider products of 1,1 forms. Now, this one were studied by Aspinwall and Kalos. They determined that this will always give rise to n equal to Minkowski vacua in 3 dimensions. And most importantly, all the complex structure moduli are fixed. So there's this constant gamma here. Its value should ensure the quantization of the flux. And as the authors determine that work, the solutions, the backgrounds that you can have to satisfy two conditions. Namely, the K3s have to satisfy two conditions. So the first one is that the K3 surfaces have to be attractive. What this means is that it essentially means that all the complex structural moduli are fixed. So these are points in the moduli space of K3s, let's say, they have no free parameters. And this means that the so-called Picard lattice of the K3, of each one of them has to have maximal rank, which is 20. This Picard lattice, it characterizes the choice of complex structure. And as I said, rank 20 just means that all of the moduli are fully fixed. For the second condition, we have to introduce the transcendental lattice of the K-tree. And for this, recall that the Picard lattice, it's defined as, this lattice is embedded into the middle cohomology of the K-tree, which is known to be even self-dual and has signature 3,19. Now, the rank of the Picard lattice is 20. It has signature 1,19, so it's hyperbolic. This will have certain implications. And then the orthogonal complement of that, simply that is the transcendental lattice. So these lattices have determinants, they have they have quadratic forms, and as such, they have determinants. And these solutions have to satisfy the constraint that the product of the determinants of these transcendental lattices is it's the square root of some integer. So this is the abstract characterization of these solutions, and it turns out that you can be exhaustive about the classification of these solutions. And this was done some time ago. Now, if you write down the transcendental lattice as a 2x2 matrix in this way, this is notation that we use. Okay, as I say, it's signature is 2,0, so it's just a rank 2 lattice. Then you can construct all the solutions up to n flux equal to 30. As I said, we are going a bit above the tadpole bound. Now, up to tadpole 24, this was already done by Brown, Kimball, and Guattari. And for this paper, we extended it a bit. So here in this table, just for reference, you have all the solutions. These are products of K-trees. So you have the transcendental lattice for each one of the K-trees. I say they would specify the K-tree itself. You have the values for gamma that you need for this to be a solution and to have the specified value of the flux. And so, yes, these are all the possibilities. But so these are the solutions for the M-theory compactifications. And now what we want to do is to uplift this to F-theory. Okay.
Sorry, can I ask you, these are solutions with all moduli stabilized, right?
Yes, these have the moduli
stabilized. Complex structure module up to and flux. Okay, thanks.
Yes, exactly. Okay, so if we want to do an F-theory uplift, what we have to do is specify analytic vibration on one of the K-trees. This is enough to have the uplift in this case. And the way to do it is as follows. So what you have to do is find an embedding of the hyperbolic lattice, which is the even self-dual lattice of signature 1,1. You want to embed it into the Picard lattice, which, as I said, has signature 1,19. If you find such an embedding, then you automatically are allowed to write the Picard lattice as an orthogonal sum of that hyperbolic lattice and another lattice, which is so-called the frame lattice. So this hyperbolic lattice is specifying the base and the fiber class in the K-tree, and the frame lattice will encode the information about the singular the singular fibers in the vibration. It also has data. It's encoding also the moduli group, and this is enough to determine exactly what is the gauge group of the vacuum that you have. Okay. And another important point is that it is the case that every attractive K-tree, meaning with Picard with Picard rank 20, it will admit analytic vibration. So there's no question of we being able to do the uplift. The task that we have, in fact, is to determine every possible value, because the embeddings of the hyperbolic lattice into the Picard lattice are generically too many. And we don't have control over that, really. It's problematic. The Picard lattice has signature 1,19, so it's hyperbolic. There are infinitely many roots. It's really a mess to study these embeddings. So for that reason, we turn to a different procedure that fortunately exists, which is due to Nestor Nishiyama. It works as follows. Now, you take the transcendental lattice of your K tree, and you can embed it into the E8 lattice. This whole procedure is based on embedding into even self-dual lattice, and the whole point is that such embeddings satisfy very stringent properties. They ensure the results that I'm going to mention. So you do that embedding, and then you can take the orthogonal complement. And that orthogonal complement, let's call it T0. There are many possibilities for T0, but only one is required for this procedure. Now that will be a rank 6 lattice that shares many properties with TS. You can then take that lattice and embed it into another even self-dual lattice, but this time of rank 24. And the whole point of doing this is that the orthogonal complement will have rank 18. So it's the rank of the frame lattice, or a frame lattice that you can have. The point is that by this chain of embeddings, you are able to construct again the frame lattice, but in a way that is involving lattices that are Euclidean. So the rank 24 even self-dual lattices, they are classified, they are the so-called Niemeyer lattices, very nice lattices. And they are Euclidean, so the process is to compute all the possible W's is in principle finite. Okay. What we do is that for every, yes?
In this way, do you know which elliptic vibration is associated to which W, or not? You just find all possible W's?
To know what elliptic vibration, well, what you can do is have every possible W, and this will tell you every possible way in which an elliptic vibration can be. The 80 types, it will tell you.
Okay, thanks.
So what we do is that we compute for each possible transcendental lattice. We embed into E8 and we get a T0. And this is the list. It's represented diagrammatically using some kind of generalization of thinking diagrams. So the first few, for which will appear mostly for low values of the tadpole of M flux, they only have roots. These are the white nodes. And fortunately, we only seem to require norm 4 vectors and then norm 6, so it's not that much, and we can encode this diagrammatically. And black nodes are long nodes, and the connections specify the inner products between them, and so on. And at the end of the table, we put some special T nodes that are relevant for configurations that go beyond the tadpole bound. Okay. I'll say a bit more in a moment about this. Then the strategy is clear to find all the W's. What you have to do is take one of the T nodes and embed it into all the Niemeyer lattices. But this is not that straightforward because you don't know how many inequivalent embeddings there are and so on. The strategy is to take the root part, the root sublattice of the lattice, and put it into the root sublattice of the Niemeyer lattice. This is particularly useful because Niemeyer lattices, all of them have full root sublattices, except the Leech lattice, which is not important for us. So as far as the root part is concerned, we have a lot of control. Then we have to extend this embedding by including longer vectors inside the Niemeyer lattice. And we do this kind of by brute force. You can use certain tricks to kill some redundancies, but at the end of the day, it's brute force. And when you have a particular embedding of the T-node, you can look at the orthogonal complement, and you can, in principle, determine the full W. This will give you the full data of the gauge group. But because of the volume of the computations here, we mostly, at the end of the day, we're interested in the existence of roots in the orthogonal complement to see if there are enhanced gauge symmetries. And so you record that data, and then you repeat this for every Niemeyer lattice. so you have to, sorry, for each 9-Meyer lattice, you have many possible embeddings, and then you have to do this for every 9-Meyer lattice. If you're able to do this for a particular T-node, you have an exhaustive result. This tells you every possible kind of elliptic vibration as far as the ADE types goes for a particular K3 manifold. Okay. And this is what we did for most of the T-nodes that I showed. And we find that the values always have roots. In fact, something that we computed, and I will show the data in a moment, is the minimal rank that we can have, because we're interested in how low you can go as far as gauge symmetries are concerned in the rank. But if you have too many large generators, meaning long vectors, the problem gets a bit out of control. Well, it very much out of control, and this happens precisely when you're approaching the tadpole bound. And for this, we constructed an alternative algorithm that I don't have time to explain here, and it's very technical, but it essentially does the process in a way that automatically discards embeddings that have roots, and it's trying just to find if there exists a W without roots in an exhaustive way. This kind of just no algorithm, we used it for these two encircled T-nodes, the 777 and the 888. Let me maybe go up to this table back. If you look at tadpole 23, tadpole 24, I don't have a, well, if you look at tadpole 24, there you see that it's important to study the 888. It appears as one of the K3s. So precisely when we are at the boundary here, we are very interested in what we can have. It's very difficult to have that information. So, but fortunately, with the help of that algorithm, we just answer the yes/no question, and we determine, okay, there does not exist any W without roots. So it means that every elliptic vibration will have singular fibers up to that point. And then we solve the problem in that sense. We would like to know when does the W stop having roots? When do you actually have a solution without gauge symmetry enhancements? And you have to go, well, not all the way to, because n-flux, you have to go to n-flux equal to 30, which is not that high, really. It's it could have been much larger. But there are some values of the flux above 24 for which still you don't have such solutions. Sorry. Okay. In this case, we didn't apply any algorithm. In fact, it's noteworthy to say we found an explicit construction of a W, and you can do it using the Lich lattice. This is explained in the article, but yes, you have to go to flux equal to 32 to have this. Now, let me show some data. Here we are looking at the minimal rank of the gauge algebra that you have for each value of the flux. When you start, and you have n-flux equal to 3 for, let's say, it's very high, the minimal rank. You always have E88 and something, E88 SU2, things like this. And it seems like when you are going up in n-flux, the minimal rank allowed goes down generically, but there are a few outliers. So it's not really clear what's going on there. Here again, you can see that in the flux 30, you hit the minimal rank equal to 0. Okay. And this other graph is a bit more suggestive, but I don't know how relevant. It's actually, you're looking at the minimal rank in terms of the determinant of the TS. So this looks to be more of the arithmetic. It may be suggesting something because the trend is much more marked. Yes, some interesting thing to see, I guess. Now you can be a bit more precise and ask what are the gauge symmetries that you actually have, what are the ADE types, and look for some kind of constraint that will tell you, aha, if you are below the tadpole bound, these patterns should be satisfied. And this is not so clear, in fact. What we find by recording a sample of symmetry enhancements, we find that every possible ADE type appears, so we cannot just simply rule out certain kinds of Kodaira fibers. It would be certainly interesting to see if there is some non-trivial condition here, but so far it doesn't look like it. And yes, so really the conclusion of this, the whole point is that you have a setting that is very well under control, and it's validating the intuition that you have behind the tadpole conjecture in a very rigorous way, because these results are exact, they're completely exhaustive. Okay? If you want to satisfy the tadpole bound in this setting, you need to have non-abelian gauge symmetries. And of course, you can ask, what about more general forms of the flux, like having these products of 1,1 forms? It's not so clear what will happen there. And the problem of modular stabilization is a bit more complicated, but it certainly would be interesting to look at. So yeah, that's what I wanted to say. Thank you.
Thank you, Héctor. So now we have time for a question, please. So we have already one. Please.
Yes.
Please, Xing Yan Li. Okay. So I think there is a question, yes, from. So do you have any comments regarding non-fixable clusters? So this
Okay.
So there is a question here in the chat.
Yes, yeah, I think for this kind of compactification of K3 times K3, you will not have non-fixable clusters. So they are not actually relevant for this kind of compactification. As far as some generic commentary, I don't think I have much to say.
So we have time for more question. There are no other questions. So, okay, maybe if someone wants to ask some question, can do also like after the second talk. So for the moment, I thank you, Héctor.